thank you, of course, to the CEMRACS organizer for giving me the possibility to speak here. So I will speak about a project I'm currently working on with Etienne Pardue on large deviations for Poisson-driven processes in epidemiology, and this is also the basis of the project we're doing here at CEMRACS with Brice. And therefore this will mainly be about the theoretical results, but I will also shortly explain what we're doing here. Okay, so first I will give a motivation of our research, because I assume that most of you are not too familiar with mathematical models in epidemiology. So I will first talk about so-called compartmental deterministic models. So the basis of our research are deterministic models, and we will look at stochastic models which in some sense correspond to these deterministic models. And we're interested in the long-term behavior of these models, and then we can build stochastic models out of these deterministic models. And in the first step, which we've done here is we solve these these deterministic models. They're somehow given by an ordinary differential equation, and we solve this differential equation, and that's what we've done here. Well, in the second point, I will give the general setup of our research. I will describe how the Poisson-driven models look like in general, and I will give a law of large numbers, which is an old result by Tom Kratz, which connects the deterministic models with the stochastic models. And then the main part of the presentation will be the large deviations. I will explain the rate function, which gives a measure for the deviation of the stochastic model from the deterministic model. It gives like a measure for the energy needed to deviate from the deterministic expected level. And the main result is then the large deviations principle, and from this we hope to deduce results for exiting the domain of the domain of attraction of a equilibrium of the process. Well, if time permitting, I will also talk about the diffusion approximation of the Poisson model, but I'm not sure whether we'll come to that. Okay, so I'll give you an example for a compartmental model, and we will always have this example in mind because this is a very nice and simple, well, in some sense simple example, but it has all the features we're interested in. So if we look at a compartmental in epidemiology, in a deterministic model, we split up the population, which is of size capital N, into subgroups according to the disease status of the individuals. So we have S susceptible individuals, that are individuals who are not infected and can become infected. Then we have I infective individuals, that are ill individuals that can infect other individuals. And in this model we also have vaccinated individuals. And now these populations, these numbers, they add up to N always. So now these individuals in these groups, they migrate to other groups according to certain rules and according to certain rates. For instance, we have a birth rate, so at rate mu, people are born and they all become susceptible. So mu people, mu times n people per time unit are born. And to keep population constant, we also, how does that work? Well, we also require that people die. Which one is it? Ah, it's this one. Okay. So people die, and they die out of all compartments at the same level. Then people are infected. So beta is the contact rate, so per unit time an individual meets beta people. So there's S times beta contacts of susceptible people, and the proportion of the people they meet that are infective are I over n. So per time unit, that's the number of infections. So whenever they meet that, there's an infection. Then people recover, people are vaccinated, people lose their vaccination, and even vaccinated people can become infective, but at a smaller rate. So if sigma, which is between 0 and 1, if sigma is 0, then there is no infection of vaccinated, so the vaccination is perfect. And if sigma is 1, the vaccine doesn't work at all. Okay, that's the kind of model we're interested in. Now, from this picture we've just seen, we can easily deduce ordinary differential equation. So we have these rates, and the change of S is given, well, birth, infection, death, vaccination, but also we gain from recovery and we gain from the loss of vaccination, and so on and so on. So that's a nice system of ordinary differential equations, and if you have a starting point, then this equation will always have a unique solution, such that the solution is in the region we expect. So every compartment is less than n, and the sum is always n. Okay, what are we interested in? So we're interested in the long-term behavior of the epidemic. We're interested in whether in the long run the disease becomes extinct or whether it becomes endemic, meaning that either at the end there are no more infectives, or there is a more or less constant level of infectives in the population that doesn't change very much. So for that we need to find the equilibria, the equilibrium points of the ODE. So in these models, there's always one very important number. That's the basic reproduction number. So that's the number of cases, of secondary cases, which are generated by one infective person in its infectious period, on average. Okay? So there is also a disease-free equilibrium, where there is no infectives anymore. I mean, that is very easily seen. If you put I equal to 0, I doesn't change anymore. So that's easy. That always exists. And if there's less than one secondary infections per infective in infectious period, if R0 is less than 1, then this equilibrium is asymptotically stable. Okay? So that's a very important number. In many models, it's the case that if it's larger than 1, then the disease-free equilibrium is asymptotically unstable. But that is not necessarily the case here. Here we introduce a second number, which is the basic reproduction number if we have no vaccination, which is obviously larger, because if we don't have vaccination, there's more secondary cases, because the pressure of infection is higher. So now if we're in between, if this is larger than 1, then the disease-free equilibrium is unstable. But if we're in between these two numbers, and then admittedly some other parameter choices have to be nice, then in addition to the stable disease-free equilibrium, we have also two endemic equilibria, where one of them is stable and one of them is unstable. So in this case, we have a bistability of this model. So I drew this picture. So here I've reduced the dimension from 3 to 2. That's easy because the S is n minus I minus V, because population size is fixed, and then I've replaced the number of individuals by the proportion of individuals in the population. And now, as we see here, for the parameter choices of this picture, we have a disease-free, well, here we have the proportion of vaccinated, and here we have the proportion of infectives. So on this line we have no infectives, no vaccinated, and on this line we have no susceptibles on the blue one. So we have a disease-free equilibrium, we have a stable endemic equilibrium here, and then we have this red line. So on the right-hand side of the red line, when we start on the right-hand side of the red line, we will always converge to the stable equilibrium, and on the left-hand side, we will to the endemic equilibrium. On the left-hand side, we will converge to the disease-free equilibrium. So this is very essential. We never cross this line in for the deterministic model. On the line, we have the unstable equilibrium. So if we start on the line, we converge to this unstable equilibrium. So what interests us mainly is it possible if we add stochasticity to cross this line? Okay, does a disease that should be theoretically, if you look at deterministic models, should be in the long run disease-free, could it become endemic or the other way around? Okay? So that's why the first step is to build stochastic models. So we build stochastic models that correspond to the deterministic model. Well, why do we think this is a good idea? Well, obviously, the mechanisms underlying disease transmission are inherently random. So there is some randomness in disease transmission. So in principle, a good model should incorporate randomness. On the other hand, it's of course a trade-off. If you have a deterministic model, it's easier to analyze. You can look at more complicated models. And if you have the stochastic model, you have to look at easier models. So I don't say deterministic models are not interesting, but there is a reason to look at stochastic models. And what we want to do, we want to see for specific models, but also in general, for what kind of models is it worthwhile to do the effort to analyze the stochastic model. So is the deviation from the deterministic model large, or is it small? If it's small, well, there's no need to do that. If it's large, maybe it's useful. So what we do, we replace the deterministic rates by independent, non-homogeneous Poisson processes. And at the jump times of these processes, an individual from one compartment jumps to another compartment. Okay, and in between, because in between the jump times, the compartment sizes are constant. In between, the rates are fixed, and therefore the Poisson rates are fixed. Okay, an example here, the infection rate at time t is beta times S of t times I of t divided by n. So that's the rate of the Poisson process. Okay, I mentioned these questions before. So what is the difference between the two processes for large n? Can the stochastic process change between the domains of attraction of two different stable equilibria, which the deterministic process cannot? And if yes, if so, when does that happen? And for which population size is that possible or probable? So deterministic models, we should keep that in mind. Deterministic models are only good approximation of reality if n is large. So if n is small, the influence of randomness is too large to look at deterministic models. But for n large, they can be very reasonable. But we want to know how large n should be such that the deterministic model is good, or maybe we should possibly look at the influence of stochasticity. Okay. Now, for the specific model I've shown you, we need a modification for our theory later on. Our theory doesn't work if the process gets stuck at at the boundary. It doesn't work then. So that's why we add, well, the easiest way to avoid this is to add immigration of infectives. And then we get these red alphas here. We eat well, and in order to keep the population constant, we let people emigrate. So this is kind of artificial, you know. We let only infectives immigrate, but everybody else emigrate. But you could also let everybody immigrate and emigrate, but this is a bit easier. Okay, and then if alpha is sufficiently small because of the continuous dependence of the solution of the ODE on the right-hand side, that if it's sufficiently small, it doesn't change too much the equilibrium points and their stability. So the disease-free equilibrium, which is now not disease-free anymore, it shifts inside. This one shifts a bit, and the curve shifts a bit towards the disease-free equilibrium, because the pressure of infection is larger because of the immigration. The domain of attraction of the disease-free equilibrium becomes smaller. Okay, so that's it's just for later, so that we can see what kind of assumptions we need for our results. Okay, so the first thing we need to do in order to address the questions I mentioned is, of course, we need a numerical method to solve the ODE. And that's what we have done here already at CEMRACS with Brice. So we have found a recent paper of Anguilov and co-authors who give us a non-standard finite difference scheme which is elementary stable. Well, it's non-standard because for the discrete derivatives, they replace the standard denominator h, which is the time step, by a more complex function phi of h, and they nonlinear terms in the difference equation are approximated in a non-local way. That is, they're on the time mesh. That is, they take their value at time tk and at time tk plus 1. If not, you get problems. But they proved, and that's very nice, because that's exactly what we require. They proved for exactly the kind of models we're looking at, they proved that the equilibria and the local stability is the same for the discrete scheme and for the ODE. Okay, so basically, we're interested in crossing this red line. So we need to compute this red line. This needs to be reliable. If we use a standard finite difference scheme, we cannot be sure that, well, say close to this boundary, we really get the right result. So this is very, very important for us that these people did the work for us, so that we can actually compute the red line. Well, here I cheated a bit, but in the first picture there was really the computation of the red line. Here I did some paint. Okay, so now we come to the general model. Okay, we look at these Poisson-driven stochastic processes. So D is the number of compartments, susceptible individual. N, which was constant in our case, is the population size. And then Zi of N at time t is the proportion of individuals in compartment I at time t. And the domain of the process that is important is compact. So we cannot look at unbounded domains. That doesn't work. So we have independent standard Poisson processes, and we have these jump directions and the jump rates. So that looks a bit different from what I described before, but it's actually the same thing, where it's equivalent to what I described before. It's just a time change. But this is much more convenient to work with. So here we have the jump directions, the jumps. We have to divide by n. Then we have the jump rates times n, and so on and so on. And if we replace the Poisson process by a compensated Poisson process m, then we get this part plus this martingale part in the back. And here already we see the resemblance, if we look at the definition of B, we see the resemblance of the stochastic model with the deterministic model. So this one, on average, will converge to 0. So we're left, in some sense, only with the ODE part. And that's an old result by Kratz, a law of large numbers, which says that the stochastic process converges to the solution of the ODE almost surely as n approaches infinity. So phi from now on will mostly be the solution of the ODE. So that's just another way of writing this, where this is now an integral equation, but it's equivalent. And well, we can also compute the speed of convergence. Well, this is not that's the theorem we use, but I think one could improve the speed slightly, but we don't need more than this. So now we know in some sense that the stochastic model should be close to the deterministic model for large n, but there could still be a large deviation of the stochastic model from the ODE. It's possible. The question is it probable? And for what order of n is this possible? So there is a recent paper by Campillo and Lobry. And I said that before. For small n, the deterministic model is not a good approximation. Question is how large n should be. So they showed in their paper for a specific model which doesn't quite fit our framework, but which is in some sense related to the models we look at. They showed that even for quite large n of the order 10 to the 6, that there is a qualitative difference between the stochastic and the deterministic model. So even for large n, one has to be careful. Okay, now we want to quantify the probability of these rare events, rare in the sense of deviation from the expected level. So we fix time horizon, we look at the space of Cadillac trajectories with domain in our compact set, and we equip this with a nice metric that makes the whole thing Polish, and then we want to quantify the probability that the process is in an open subset or in a closed subset of the Cadillac space. And that's as much as you can do. Okay, to do this, we have to define the Legendre-Fenchel transform. So if we are at A and move at direction Y, it's given by this equation. I don't want to go too much detail, but here we have the rates, here we have the jump directions, the direction of movement. So this is in some sense, it's a local measure for the energy needed for a movement starting at X with direction Y. Okay? So, and if we plug in theta equal to 0 here, this becomes 0. So this is always non-negative. And it's 0 if and only if the direction of the movement is in the direction of the ODE. Okay, that's important. So moving is there's always cost unless you move into the direction of the ODE. When it's always smaller than infinity, if you move into a direction which is spanned by a convex cone spanned by those hj's for which at position x the beta j's are larger than 0. So the beta j's can be, I'll go back here. So if we're at the boundaries, for instance here, we cannot move into this direction. So so at this point, the beta j for the, say, loss of infection, the rate is 0. So if this is x and y goes this direction, this will be infinity. And I mean, that's what we need. It needs to be infinitely expensive to move outside of the of our compact set. Okay. And with the transform, we get the rate function. The rate function is now the energy required for a deviation from phi, which is the solution of the ODE. So it's the integral over the function, over the transform, if we are at phi tilde of t and move into direction phi tilde prime of t. Well, this only exists if phi tilde is absolutely continuous. If it is not, well, and starts at x, so if it doesn't start at x, we say it's infinity. And if it's not absolutely continuous, we say it's infinity as well. So the rate is only finite if the function is absolutely continuous. And it's 0 if and only if phi is the solution of the ODE. So this gives us the costs for following phi tilde, which is free if we follow the ODE, and the more we deviate, the more expensive it gets. Okay, and so the main result which we're working on is the following. Well, for appropriate assumptions, and one of these assumptions I showed before, we should not get stuck at anywhere. So we always have to have the possibility to move away from each point. And well, then there's some technical assumptions. Then we get the so-called large deviations principle for the model that we have. And we have to be careful. So this is work in progress. We have accomplished most of the proof, but there is still 1-2 technical bits missing. So it's not completely finished, but we're very confident that it's true and that we'll finish it soon. So now we can bound the probability that Zn is in an open set of the path space with the help of the rate function. And we can bound from above the probability that Zn is in a closed subset of the path space with this thing, which means that well, for any set D, well, it needs to be measurable, of course. Of this open thing, well, so this is larger or equal minus Is there something wrong? Yes. Well, then there should be a lim inf, then a lim sub, and so on. And hopefully now this is smaller or equal. Thank you. Okay, so now we can find for every set, we can find with this help some bounds, and that's as good as you can get. So the problem for proving this theorem is that, as I mentioned that before, our rates approach, or they can approach 0 if the position approaches the boundary. So they're not bounded away from zero. And there's existing theory if the rates are of this kind, if the rates are bounded away from zero everywhere, but if not, this comes well, very, very, very tedious, I must say. So that makes the proof, it makes it technically very, very unpleasant. So that's the main problem here. I won't go into much detail about the proof. Okay, so now, but before I said we're mainly interested of this exit from domain problem. We want to exit the domain of attraction of one of the equilibria, the endemic equilibria or the disease-free equilibrium. So we say that G is the domain of attraction of one of the two equilibria, and we're in the domain of attraction. And the question is, when does the process exit from G and enter the other domain? So this is the tau n. And we're also interested in the question, where does the process exit G? And on which trajectory does it do that? And well, if I mean it exits G, I don't mean that it hits the blue boundary or it hits the black boundary, but it hits the red one. Okay, and how do we quantify this? Well, we quantify this. Well, in order to find a result for the time and the place of exit, we need to solve somehow optimization problems. So the V here is the minimal price, the minimal energy needed to move from Y to Z in time t. Okay, this V without the capital T is the minimal energy needed to move from Y to Z in any time. And this V bar, which is the important quantity, is the infimum, the minimal energy needed to move from the equilibrium point to a point on the red boundary. Okay? So what happens is that the process, well, it is attracted by the boundary, so it will move for a very, very long time very close to the boundary, and then at some point it will deviate from this equilibrium point, and it will move to the boundary, and it will use the cheapest way to do that. Okay? So it will use the cheapest phi such that it can go from X star to Z. Okay? And then we get the following result, and well, this is also work in progress, but it relies on the large deviation principle very strongly. Once the large deviation principle is proven, this is merely, well, it's not trivial, but existing results can be applied in a not too complicated way. So that follows as soon as the other theorem before is completely established. So in this sense, we get that the probability, so we have this V bar. So the probability that the time of exit is smaller than e to the n times V bar times e to the n times delta converges to 1. That is, well, informally, that means together with the second result that the time of exit is about, for large n, well, of course, for n large, and one has to be careful, but it's about this quantity, so it's exponential in the V bar. Okay, well, and then we have a last result about the place of exit, and well, this tells us if we take a a closed set on the boundary, and the infimum, the cheapest point to exit the domain, is not on this closed set, then the process will for large n, not enter there. But if you find a unique minimizer of this, and we call it Z star, then the place of exit will most likely be very close to that. Okay, so that's what I said before. So it will it will use the cheapest trajectory and will use the point which is cheapest to exit the domain. Okay, unlike the other result here, where this of course relies also on the first result, on the second result, so this has to be proven first. And the difficulty here is that this red line is the so-called characteristic boundary of the domain. That is so these exit from domain problems are easier if from the boundary of the domain that you want to leave, you're drawn inside. And if you're not, they become more complicated. So here, you're not drawn inside. So that's the difficulty here. But well, this we'll tackle later. But that's what we want to prove next. Okay. So we're mostly done here. Before I talk shortly about the diffusion approximation, I'll have a few comments about the simulation we're interested here. So first we computed the ODE with the non-standard difference scheme. Then simulating Poisson process, the Poisson model, that's not very difficult because the process, the rates of the Poisson processes are constant between jump times, so you just iteratively let processes jump, and then that's not very complicated, but a bit time consuming. And then the next thing we do, we want to compare the numerical results we have with our theoretical results. So for that we have to solve these optimization problems. So currently we're trying to solve these optimization problems to find, numerically, to find the time of exit and the place of exit via solving these problems. And that, at the moment, we do by discrete time dynamic programming. So that means we're kind of doing a backward induction. That should work in theory, and the schemes we've programmed are not very reliable. So the discretization in space and time we do is not very good, so we have to work on that. But that's what we're doing currently. Okay. Given the fact that we can finish these simulations and these numerical things, we might also try to simulate the diffusion approximation of our Poisson model and compare this stochastic model to our model. So this is a object which was analyzed by Kratz as well a long time ago. So in a sense, we had these compensated Poisson processes here, and now we have independent standard Brownian motions. Okay. And this can be written as a diffusion in distribution. And then Kratz showed that this diffusion approximation is close to the Poisson model. So there exists a random variable with distribution independent of n, and which has this nice moment for some lambda, such that for fixed capital T, the supremum norm deviates less than x times log n through n. That is, for n going to infinity, this vanishes because in distribution, because the distribution of x does not depend on n. So that's at first sight very promising and interesting. There's one problem with Kratz's theorem, because well, it's only uniform for fixed t. Okay, so it does not really explain how close the processes are in the long term. And well, if we're interested in the long-term behavior, we're interested in the exit from domain problem, and for a relatively simple model, Dahmen and co-authors have shown in 2010 that the two processes with respect to this property, they do differ, and they do not only differ quantitatively, but they also differ qualitatively. That means they don't not only find slightly different times of exit, they also find different places of exit. And that's why one has to be very, very careful with this object. Nevertheless, it would be nice to see the difference between the Poisson model and the diffusion approximation. But well, unfortunately, I'm not too confident that we'll get to this next week, but we'll see. Okay, that's the end of my presentation. Thank you very much.
Are there questions or comments? So I have some. So first, I would like to, I'm not sure to understand precisely how the result you mentioned by Campillo and Lobry about the fact that the stochastic process can deviate even for a very large n from the deterministic model. Yes. How do you see that from the large deviation principle? How can you relate that to the large deviation principle?
Oh, no, that's just a reason why we think it's worthwhile to study the stochastic model, because the deterministic model may deviate even for large n. So that's just a reason why it's important to study stochastic models even for large n.
Because wouldn't you expect in this case that the rate function is actually very close to 0 or something like that for some trajectories, and that you have a very low cost to move from a place to another?
In the specific paper,
yeah.
You mean? I have not thought about that.
I also have another question. So you mentioned in the end diffusion approximation.
Yes.
So and you also mentioned that for large deviations principle for Poisson processes, it's a difficult question.
Yes.
So, but for the diffusion approximation, is it an easy problem to have a large deviation principle?
We first thought it might be easier. So that's why Etienne came up with this diffusion approximation, because so large deviation principles are much more well known for diffusion processes. But if you write this as a diffusion, you have non-Lipschitz coefficients, so you have square roots. So that makes it already a bit difficult. Plus, you still have the problem with the boundary. I'm not sure how you would tackle that. So it might be easier. I don't know that, but it's far from being trivial, I think. We have not. Well, we first wanted to do that, but then we realized, well, they're not. They maybe that's not the right approximation. And then we looked up the literature, and we found that indeed, for what we want to look at, in some cases, it's not the right approximation of our Poisson model. So, but that was what we wanted to do first. But I don't think it's trivial. Indeed, I think that Etienne has, in a one-dimensional model, he is tackled for a specific model. He has tackled this problem and solved the somehow the exit from domain for this problem. But well, I haven't done that.
Okay, but in one dimension, it's. I mean, you just want to know on which side of the.
Yes, it's a question
the
was when
interval
does it
you
hit
leave.
somewhere?
Okay.
That's what he
Right, so
did.
then, okay, you can make computation specific to one dimension.
Yeah, well, I've not read what he's done,
Okay.
but he told me that he's working on this, and he said that they've accomplished that.
Are there other questions? So if it's not the case, thank you again.
Thank you very much.